So we'll see how these kind of device are quite similar with BJT, but has a little bit different operations. The learning objective for this subtopic is basically to describe the basic operation of Mosfet, analyze the biasing circuit for Mosfet, as well as find a cue point for the Mosfet to act as amplifier. So as same as BJT, so basically this is the first part that we learn the DC analysis of this kind of device. Actually, the main point is to find the cue points, where this cue point will basically determine whether we are doing the proper biasing or not. Okay. Practically, cue point we normally is at the middle of the DC load line, typically. Well, when we talk about field effect transistor or FET, so basically we can divide FET into several types, which is what we call as a JFET, and then we have a MOSFET, and because we already covered the MOSFET, E MOSFET. Okay, so please, we only covered MOSFET, E MOSFET, and typically more on N channels. All right, so this is only one, but I will also explain a little bit on this MOSFET. What is the difference between the D MOSFET as well as E MOSFET? Okay, so the first three is not covered, but we go to a MOSFET, which is metal oxide semiconductor field effect transistor. So we can divide this MOSFET into D, which is a D MOSFET and E MOSFET. D MOSFET refer to depletion type of MOSFET, where this kind of MOSFET can operate at both regions, negative, positive VGS, while E MOSFET, or known as enhancement type MOSFET, is basically working only at one region, whether it's positive region or negative regions, depend on the type of MOSFET, whether it's a P type or N types. So the few difference between the BJT and MOSFET you need to know is basically in terms of the operations as well as other electricals or physicals behavior. Okay, first one is basically when we compare with the BJT, MOSFET has a more static sensitive, while BJT is less static sensitive. All right, when we talk about static, it's basically it refer to the basically the charge, the outside charge. Okay, let's say if you are going to manufacturers or and industries, before you enter the experimental space, so basically they will check for the static charge. Okay, if your body normally contain a static charge that you not even realize. Okay, so they need to basically measure your body and find out whether your body or your all the wearings have this static charge. Okay, this static charge is very dangerous because it can destroy the component. So basically, compared to BJT, MOSFET has more static sensitive because when we talk about MOSFET is basically a voltage control device compared to BJT. BJT is control device, So your input is always IB, the base currents, and will be amplified to be into collector currents. But for the MOSFET, your input will be voltage, which is a VGS, and your output will be current, which is a drain current ID. Compared to BJT and MOSFET, so basically MOSFET has the advantage in terms of the less sensitivity to temperature variations. Okay, BJT is sensitive to temperature variation because this current control device. When we talk about current control, so basically when the electron receive more energy, so basically the behavior will be changed. So basically, BJT will be more sensitive to temperature variations. And then BJT is current control device, MOSFET is voltage control device. And we'll see later on how it different in terms of the constructions of these two components. For the BJT is basically a bipolar devices, while MOSFET is unipolar. The meaning of bipolar and unipolar here is basically for the BJT, the current produced by the BJT is basically contributed by both major carrier of the material, which is electron as well as holes. So basically both carrier will contribute to the forming of the currents. However, for MOSFET, it's basically unipolar, so only the major carrier will contribute to the formation of the currents, whether it's holes or electrons. And some similarities between BJT and FET is basically it can be used as amplifier, switching devices, as well as impedance matching circuit. Right. Here is advantage and disadvantage of MOSFET that you can go through. So we go to advantage of FET or Philip FET transistor, where it has a higher input impedance. Okay. Why higher input impedance will actually helps the component to be better in terms of interconnections. So let's imagine, okay, if you have any load, for example, you have resistance, it has certain R, and this resistance is connected with your device. So it has a very high impedance. So whatever, when you connect the very high impedance with a load, so basically the load or the total impedance looking from here will be almost unchanged because Z will be very big. So we can see that when FET has a very high input impedance, so basically the loading effect will be less. So basically loading effect is something that we will learn when you enter the instrumentation lab. So you have an experiment on loading effect. Loading effect when you want to measuring a voltage or current using analog as well as digital devices. So you can see by using analog, the efficiency will be less. Because what? Because the device itself has certain load that need to be considered. When you connect parallels to measure the voltage, of course, the total load will be less than what is intended or measured. So basically this MOSFET is good because it has higher input impedance. So when we connect, so the load that we have here is almost unchanged. And then FET also less sensitive to temperature variations. That means the Q point will be more stable. And also MOSFET is easily integrated to IC. Do you know IC? Okay. or we call a chip, because in ICs there are a lot of component, typically the semiconductor component inside the chip. Due to the compact size or very small compared to BJT, so basically MOSFET is more suitable for IC design. And then the FET is less affected by noise. Noise is basically unwanted energy that coming into our systems. Okay, noise signals can come from basically the connection of the device, the temperature, and outside energy. Okay, so the noise basically will degrade our performance of the device itself. And then it's more suitable as a logic switch due to no offset voltage. So the voltage is very accurate. So it's very efficient as a logic switch. So we're not covered about the switch in this topic, but it's more on whether our MOSFET can be used as amplifier or not. And then you can see some disadvantage here. For example, more sensitivity and static charge compared to BJT, low gain bandwidth product. So that means compared to BJT, MOSFET has a narrower bandwidth. Bandwidth is basically operating frequency that basically uh, the device can cover certain gain. Okay, if you still remember how we plot the frequency response of the BJT in our last subtopic, we can see that we have a lower cutoff as well as high cutoff of the BJT. Okay, due to the capacitor of the circuit. So basically, it has a quite high bandwidth for BJT, but for MOSFET is a little bit low, both gain and bandwidth. And then other is a low high speed switching performance at high frequency. So this is basically uh, switching performance, whether it's a high speed or not. So basically it's low at highest frequency. And then low high power handling capability means that the device cannot handle more power compared to BJT. So it's basically a small power devices. So what happens if we supply with a high power? So basically the device can be easily damaged or burned out. Okay. Right. Am I still here? Are you still there?
Yes, right there.
Okay. So my connection is okay because I cannot see anything. I don't know whether I still in the connection is still there here or not. All right. So we continue with the basic construction of MOSFET. Right. Hopefully you still remembered how we construct a BJT. So BJT is basically the combination of two PN junctions, whether it's NPN or PNP, and then the body of each part is connected with one terminal. For example, we have I draw back. For example, we have NPN. So one is connected to base, one connected to collector, one connected to emitter, for example. All right, this is for BJT. So here, for the MOSFET, you can see we still use the semiconductor material where we have P-type or N-type, right? But it has a little bit different constructions. Please remember this because maybe you will be asked about how we construct the MOSFET. Right, so based on the figure, we can see that we have the same semiconductor material here. That, for example, we have a P-type. Okay, these two basically semiconductor material will be connected to one terminal each, which is a what we call as a source terminals, S. And then we have drain terminals here, D. And basically the output of this device is basically controlled by the gate terminal G at the middle. Well, basically the gate terminal, we were connected to a metals here. And most especially, yes. All right, so basically, you can see here the gate is connected with a metal, and then we have one dielectric layer, okay, built up by what we call as a gate oxide. Okay, this gate oxide basically will separate between our metals here as well as our semiconductor material. So there is no direct connection between gate and the body. Well, knowing that, so basically, we can predict that there is no current flow that can flow through the body from the gate. So how we can control the current, the output current? So basically, we control by using voltage, right? So there is no currents, okay? Ig equal to 0, but we have voltage. For example, if you supply positive here, it will be negative here. Right, so basically, there is no direct connections between drain and source. We can see there is no direct connection between these two. So, knowing that, actually how the current can flow from the drain to the source, there is something that you need to understand how we can create the basically the road for current to flow. So basically it's based on the gate. Okay, when we supply the voltage, so basically the voltage, when we have a positive, the voltage, so it's pull some electron from the n types to be near this place. So it will create some road here to connect between the drain terminal as well as source terminals. Well, we can say that knowing this, since the gate is 0, so we can say that the current from the drain and source will be identical or the same current. So it will be easier for analysis. So you have to differentiate between the N and P channel of the MOSFET. All right. For the N channel or N MOSFET, the source and drain are N types, okay? And the body is P type. If the MOSFET is a P channel or P MOSFET, then the source and the drain are P types and the body is N region. So if we see this picture, basically this is a P type. P type of MOSFET. Because drain and source are connected to with a P type. And the body is N type. So please remember this. And basically this N and P MOSFET basically have a different polarity in terms of the supply voltage. Okay. For example, we have VGS here. The VGS if positive will be positive when we operate with an N type or N MOSFET, and it will be negative with a P MOSFET. That's all. But the current, the ID equal to IS is always positive.